Well, our speaker is Steve Dittmar, our very own. He has been a software engineer with IBM for almost 20 years and really enjoys how modern astrophotography combines astronomy, photography, and technology. For similar reasons, he volunteers as the MHAA Webmaster and is building the new MHAA website launching soon. Steve grew up in the central region of New York where skies were fairly dark. His first scope was a department store telescope that wasn't great for much beyond the moon. But with a lucky glimpse of Jupiter and the Jovian moons and seeing the two impressive naked eye comets, Hyakutake and Hale-Bopp, the 1990s sparked a curiosity that never faded. Wanting to re-enter the hobby, he attended the Northeast Astronomy Forum for the first time in 2014. He enjoyed it so much, he impulsively dove headfirst into a complete astrophotography rig that same day, scratching a decades-old itch. Since then, Steve has attended multiple astrophotography workshops, and in 2017, he traveled to Nebraska to witness his first total solar eclipse. To his delight, astronomy continues to deliver awe-inspiring, memorable experiences and new friendships with no end in sight. He has since expanded his astronomy gear to include binoculars, solar scopes, tracking mounts, and a small array of cameras. He enjoys the challenge of imaging the full variety of night sky and solar object and is guilty of sometimes loving the learning experiences more than the practice. And he's been a member of MHAA for how long, Steve?
What's it been, 2-3 years now?
Okay.
Yeah.
Cool. All right. Take it away.
All right, thank you very much. Let me go ahead and get these slides up.
Oh, I got something here.
All right. Okay, so thank you for the introduction. As she said, my name is Steve Dittmar, and today I'm going to talk to you about intermediate level astrophotography concepts. In my opinion, to kind of graduate from beginner to intermediate, you have to sort of be able to recognize the flaws in your images and understand the cause and implement their solutions. But how skillfully and consistently you perform those tasks kind of determines when you've become an expert and moved on from intermediary. Most people spend quite a long time in the intermediate level. I would say I'm there, and some people peak there, and you can still produce fantastic results at that level. So not everybody has to be an expert. But the goal today is to familiarize people with, people that are beginners or early on in their astrophotography hobby, of some of the higher level concepts and tools and hardware that you'll kind of inevitably come to rely on. And being aware of what's available and how things work a little bit more will hopefully save you some time and frustration. And there's plenty of frustration to be had in this hobby to begin with, but hopefully we can save you some of that. So to get the most out of it, ideally you can already set up and take night sky images with your camera, and are at least familiar enough with the night sky to locate Polaris. Hopefully you'll come away understanding what it takes to image smaller, fainter objects, how to reduce some imperfections in your images, and improve your astrophotography vocabulary to make it easier to ask the right questions when you run into issues that you can't necessarily solve on your own. If you feel like you're missing some basics after watching this, a friend of MHAA up in the Adirondack Sky Center, Seth McGowan, did a presentation for us in January that was intended for even earlier beginners that are really truly entering the hobby now. So if you feel like you're missing some key steps, check out our YouTube page and find that video from Seth, and you can pick up there what you're missing. So we'll cover some of the topics you see here, possibly a little bit out of order, just because sometimes it's hard to talk about one without kind of referencing the other. But in general, we're going to go over the types of astrophotography, a little bit about mounts and alignment and guiding, why they're important, cameras and filters and how to compare them, calibration frames and the effect that they have on your final image. We'll touch on some optional equipment, some more jargon, and a little bit on general troubleshooting. So first, the types of astrophotography. and how and why some of those processes are different. So when I was beginning, I kind of assumed naively that deep sky objects were all smaller and dimmer than anything else that we'd be targeting within our solar system. Obviously, that's not entirely true. So I took this image of Orion Nebula, cut off a bit at the top with my compact DSLR, and we used that kind of as a starting point for comparing the sizes of these objects. So I cropped and adjusted the image and added the lines to make it easier to see, where that actual constellation is. So within Orion's sword is the Great Orion Nebula. I took that shot with the same camera and just a longer lens. Excuse me. And then after that, we have the first astrophoto that I ever took, which was actually using a friend's Canon DSLR on my 8-inch SCT, and that's using a focal reducer as well. So that's out to about 1400 millimeters of focal length. So the first one was at about 19 millimeters, second one was about 55, and this last one was about 1400. So with all that magnification, you might think that this nebula is really small, but it's actually larger as seen from Earth than our full moon. So it's deceptive partly because our eye cannot see the outer wisps of the nebulosity, but even looking at the image side by side right here, you might still think that the moon is maybe about as big as the nebula, But if we draw the outline of the nebulosity, you can see it's a little more obvious that actually that nebula is almost about twice as wide if you were to put two moons kind of side by side in there. Now, if we compare Jupiter, our largest planet in our solar system, but it's extremely tiny compared to either of those targets. And then obviously the sun, don't really have to compare that. We know that's the same size as the moon, and hence why we get those beautiful total solar eclipses here. So to be clear, there are plenty of deep sky objects that are even smaller than our planets, like the Little Gem Nebula. But initially, I would have never guessed that some of them actually appeared larger than our moon in the sky. And another great example too is Andromeda Galaxy, which is actually about 6 times the width of our moon in the sky. So how do the kind of trials of one type of photography compare to the other with these different targets? So ultimately, longer exposures and higher magnification make it more critical to have good polar alignment tracking. And longer exposure also introduces more types of noise, more of certain types of noise. Brighter targets are going to require very fast exposures, so noise is not as much of an issue, but you often need to reject a large amount of light to avoid the overexposure. In the case of the sun, you actually need to reject an extremely high amount of the light energy just to be imaging it safely. The planetary imaging is unique in that the targets are extremely small and fairly bright. So anytime you're imaging minute details, whether it's on a small planetary disk or the minute details of the massive surface of the sun, the atmospheric turbulence and the seeing conditions can actually have a big effect on how well you can see those details. So the higher magnification needed for tiny objects also makes for chromatic aberration to be more noticeable. Those are all kind of issues that you kind of run into in the different types of photography. So for solar and planetary imaging, I didn't realize at first either, and sometimes lunar, that you actually often use video instead of single frames captured one by one. If you could do short exposures that could capture enough light to reveal dim space target, deep space targets, we'd use video there too, but realistically, it's only practical for bright targets. So because it's so easy and fast to capture a ton of frames and more data allows us to increase the signal to noise, we use video's high frame rates and extract the individual frames later to be stacked. So with a large target like the sun, assuming you aren't trying to home in on a small feature of it like the sunspot, we generally capture the cameras at the full frame when we're taking those images. But for small targets like the sunspot or planet, if your camera supports it, you actually define a region of interest around just that planet so that only the small portion of the sensor needs to be read, which can then significantly increase your frame rate and you can capture more data faster. So in this image, I was actually capturing just a 480 by 640 pixel region of interest at about 73 frames a second. The camera sensor was actually a full 20.2 megapixels. So 480 by 640 out of about 5,400 by 3,600 pixels. but everything outside of that region of interest was useless and not worth capturing. So it's convenient and more efficient to be able to do a region of interest. So let's just go quickly over the, well, not quickly, let's go into the high level steps and how they make a difference on your final image. So I mentioned signal to noise a little bit before. Noise is imperceptible if the image is sufficiently bright, like in a daytime photo, and because there's a very high signal relative to that bit of noise. With astrophotography in a 5-minute exposure, a 10-minute exposure, it can actually look like a pitch black rectangle as your final image because the amount of light that you're capturing is so low. So that means that even a little noise becomes more noticeable. So the definition of signal to noise is the ratio of the signal that you actually want to the noise, which is the signal of other background energy that you don't want. So with imaging, that becomes the light, the photons you're trying to receive from your target is the signal, and then the background noise from the electronics and from other thermal inputs are the noise that you don't want. It's injected into the images from imperfect hardware. In the perfect world, the sensor wouldn't get warmer as you do a longer exposure, so it wouldn't be seeing infrared energy coming off of those chips. You wouldn't have a warm amp spraying light onto the sensor and giving you amp glow, stuff like that. So the goal is always to increase the signal to noise ratio in the final image. So noise in general is the presence of a brightness or color that's not part of the image you're taking. And digital cameras contain more noise in darker regions, which is actually opposite from regular film, which used to get more noise in white, brighter frames. That's just the nature of the way that the light's kind of collected in those mediums. So sometimes you hear the frequency or the intensity of noise. And there's two different kind of types of noise. There's the chroma noise and the luminance noise. Chroma noise is just the color, these random different colors that you're seeing here that are not part of what you're trying to image. And the luminance noise is these bright spots that that you're not trying to image. You get both of them combined usually in your images. If it's high frequency noise, that relates to how frequently the pattern or the little splotches repeat over a given area. So you can see that this one is very fine-grained, high frequency noise, whereas the one below it, the noise is a little bit larger, and so covers more space for any, each splotch is a little bit bigger, which makes it a low frequency noise. So given the same area, you've got fewer of those splotches because they're bigger. So if we could boil it down to 3 steps and ignore the fact that there's actually many small steps underneath them all, it's aim, capture, and process. But each of those steps, those sub-steps, really are important for limiting the amount of extra noise and the other imperfections that we're allowing into our image. So on the aiming side, precise aim allows you to take longer exposures, and that allows you to collect more signal, which allows you to defeat the noise better. You want that signal to noise ratio to be higher towards the signal. So the aiming matters for that. If you're not able to aim precisely, it's going to streak across the field of view, or it's going to be bloated, and you're going to end up having a harder time. The signal is not going to be as defined. On the capture side, using the right cameras and filters allow you to capture signal more efficiently and reject noise more efficiently. And then on the processing, that allows you to remove the unavoidable noise from the gear, the imperfections of the hardware, and the imperfections of the glass, etc. And then you could technically add another step into the processing side, which would be an advanced post-processing that you would do after calibration frames for even more noise reduction. And that's kind of beyond the beginner intermediate discussion, so I won't really get into it. That's where you're doing stuff in like PixInsight and other processes that gets a lot more complicated. It has its own learning curve for another day. So just to kind of compare the signal from the same shot, one taken as a single frame, 60 seconds, versus one at 300 seconds. And what you see is that the noise from the 60-second shot is more noticeable than the noise on the 300-second shot. And this is without any calibration done to it. It's just stretched to make it visible from the histogram, but we didn't do any calibration frames to try and clean it up at all. So there's more like color fine grain noise over here. This is even finer grain noise, and it's a lot smoother in these dark areas. So from the polar alignment, the foremost after setting up your telescope, you do the polar alignment, and the goal is to point your mount at your celestial pole, which is roughly Polaris in the northern hemisphere, so that your mount can rotate at the exact same speed as the Earth, but in the opposite direction, and at the same arc to counteract the Earth's rotation. So if you're imprecise, your target's going to slowly move across your camera's field of view and cause star trails or unsharp images. Just a quick note on the equatorial coordinates, because that was something when I was first kind of going from beginner to intermediate level, I didn't really fully understand exactly what right ascension was and how that all fit in. So I'll just touch on that. These are commonly used for coordinates in astrophotography because they're mapped to the celestial sphere, and the right ascension and declination are to the celestial sphere. Celestial sphere, what longitude and latitude are to the Earth's surface, respectively. So objects on the celestial sphere are typically moving, but their coordinates change so slowly compared to Earth-based systems like altitude and azimuth that you can plan out where it's, you know where it's going to be relative to the other stuff in the sky well ahead of time, and you can plan to look for it in some place, no matter what time you're going to be out there, as long as it's dark enough to see it. When you use altitude and azimuth to reference where something is, it depends heavily on what time you're outside, because you're using coordinates that are mapped to the Earth's surface and projecting them up onto the sky. But that's constantly, moving quickly. So the right ascension is the position around the pole that you've gone to, or that you're going to, and it's just the circle. It's the number. It's listed in the sidereal hours, minutes, and seconds. Kind of like a clock would be. Doesn't matter how far away you are from the pole, it's just about that one direction, that one axis. The declination, and that goes from 1 to 24 hours around the whole, the whole pole there. The declination is from 0 to 90, and 0 is at the celestial equator, 90 is at the celestial pole, positive 90 if you're to the north, negative 90 if you're to the south. Go back one. So when you're moving in this coordinate system, you're basically just looking at how far away from the celestial pole is the object in the declination. And then if I rotate around from that position, where along that rotation is the object. But what's difficult about the RA system is that 0 hours is not an obvious spot. 0 hours is actually listed as the right ascension of the sun on the vernal equinox on March 21st. Well, that makes it kind of tough to have a reference point at night if you're trying to say where is 0, because you can't see the sun at night, hopefully, and you can't really necessarily see where it would be on a specific day if it's not exactly that day either. So it makes it a little tough to look up and say, where is something. So what I usually use is the Cassiopeia's chair asterism. It's actually the eastmost star, which is where this red line is pointing, is actually very close to 0, and it's always above the horizon for people in the north here. So it makes it a convenient place to look at if you're trying to find 0 RA and use that as a reference point. Polaris alignment scopes definitely kind of threw me off when I was starting, partly because there's a handful of different styles, and I didn't really understand what I was looking at. So I'll explain those a little bit. So the scope that we see here is an ioptron style polar scope chart. And the reason we need them, the reason it's not just a crosshair in your polar scope, is because Polaris is not actually dead center on our celestial pole. It is moving closer, but it'll be quite a while till it gets even closer than it is today. So we need to polar align Polaris to be on the circle that it's taking around the celestial pole, and not put Polaris dead center in the crosshair itself. So the line that comes out of the center of the crosshair there leads to an X, and the X, when you're looking through your polar scope on your mount, is where Polaris needs to line up. Because Polaris is moving, like I said, closer to the celestial pole, the ioptron chart actually includes a little legend in the top right corner that shows, relative to those concentric circles, how far inward, closer to the dead center of the pole, Polaris will be at each of those years. So if you were lining this up in 2012, it needs to be lined up on the outermost circle. But if you're lining it up in 2028, it needs to be on the innermost circle. And this chart kind of shows you up to 2032. So after that, you might actually just need to replace your polar scope. And speaking of the different styles of polar scopes, this is a Celestron polar scope. It's a little less precise. And the way this one works, you just rotate the polar scope until the Big Dipper is in the same orientation as it is in the sky when you're doing your alignment, and then line up Polaris to the Polaris circle as it's marked. That one doesn't have those gradations for the different years as it moves, so potentially that scope, that polar scope, could need a replacement sooner than the others, depending on how precise you need to be for what you're doing. And then this is a Takahashi style. I've never actually looked through a polar scope of a Takahashi before, but it's very similar to the ioptron in that it shows the concentric circles, and those represent making it easier to figure out where Polaris needs to be as time goes by, as it moves closer to the actual pole. So real quick, talking about the mount technologies. Again, this was something when I was kind of working through all this stuff, I'd heard a lot of these terms, but didn't necessarily understand how they were different. So the kind of simplest mounts are alt-azimuth. They move very much in the way that you would expect them to, up, down, left, right. It's very natural to aim with those as a human. But there's different types of them. So the alt-az that's kind of defined for actual astronomy tend to be more like the one on the left, where they're going to have more support for the gear that you're putting on top of it. There's room to have a camera and maybe have some other kind of either rail system or something else to support the lens if you have a longer lens or a small telescope on it. If you see a pan tilt, that's more of a videography, photography term type of mount. It's usually just got a single screw at the top to mount the body of the camera, but it's not necessarily intended to support something much larger like an actual telescope hanging off the front. Then you've got the fork mounts, which attach to the telescope from the sides. You can have one or two arms on those. They're most often used with a compact scope design like an SCT. For visual astronomy, they're great. They're not always great for astrophotography because particularly if it's an SCT in this kind of a setup, your camera is going to be hanging off the back of this, and as you go towards zenith, you could slam it right into the bottom of the mount. And then lastly, you have the Dobsonian mounts, which is kind of similar in a way to the fork mount, only with the base on the ground. These are usually used with something like a Newtonian, where you've got the exit where the eyepiece is going to go is towards the front of the scope, and the scope is longer to begin with. If it was, an STT style on a Dobsonian mount, you'd be laying on the ground to try and see through it, so that wouldn't make much sense. All of these, because they move up, down, left, right, you could technically motorize and track them to a target in the sky, but you're going to have field rotation. So even if you followed it as it moved around Polaris, that object is pivoting and rotating itself, in your field of view, and your camera is not rotating with it. So that limits how long you can take an extended exposure on a mount like this. So trackers are kind of the next level up. They're motorized only to move in the right ascension axis to counteract the rotation of the Earth. They're generally useful for kind of shorter focal lengths, maybe like 400 millimeters or so. After that, you kind of have to get really accurate with your polar alignment, particularly in the declination direction, because even though some have an auto guider port where it can have assisted guiding to enhance the tracking, it can only correct errors in the RA, in the right ascension. It doesn't have any ability to move and correct in the declination. So that, again, if you have a higher magnification, is going to limit how long you can do an exposure without it's kind of smearing across your field of view. Usually these, you'll have the rotation surface, and then you'll attach like a ball mount to it so that you can attach your camera and point the camera at anything in the sky. If you put the camera straight to the rotating surface, you're going to be fixed and only pointing in one direction. So that's almost, that's almost always how they're used, is with a ball mount. There are versions that, like this one in the center, that have counterweights, and you can put a slightly bigger telescope off the front of that, or other adapters where you can actually do multiple cameras at the same time, etc. Push to and go to confused me when I was getting into this. It sounded like the same thing, so it didn't make sense to me why they were different. But real quickly, push to is computerized mount technology using sensors to recognize the mount's movement, but with no motors to drive the movement. The controller tells you where to go to, the directions to push the scope, but you manually push it there to the target. Go to is the same concept, only it has the motors to automatically move it for you. As far as I know, either style could technically go onto any type of mount, but push to seems to be less common than go to these days. And commonly, if I see push to, it's usually with a Dobsonian mount, and I think that's just because they're easier to modify, and a lot of Dobsonian mounts tend to be homemade, so it's an easier modification for them, for people to add to it. So then we get to the German and Chinese equatorial mounts. These are kind of the go-to for deep sky astrophotography and more extended exposures. They both work in a very similar manner of rotating around the right ascension axis and having a second axis to rotate around the declination axis. They're almost always motorized, as far as I know, in both directions, although I've seen a couple that aren't. And once they're polar aligned, it's going to rotate around the celestial pole with the right axis, and your declination axis, if it's aligned well, should never have to change either. It can be confusing to manually point to the scope to your target when you're using a gem or a SEM, because you can't just push it up, right, or left, up, down, left, and right like an alt azimuth would. It has to be within rotational movements. They're designed and therefore ideal for astrophotography because the tracking does naturally counter the Earth's rotation without having to deal with field rotation. It takes care of both of those in one setup. The SEM, the Chinese version, is a newer design. It places the center of mass closer to the center of the tripod support, which then requires less counterweight and reduces the moment of inertia during guiding pulses, which makes the guiding pulses less violent. This also supposedly reduces the energy needed to track because it's not having to move as much weight out at the end. And that results usually in longer battery life when you're out in the field, which is good. And it does, then reduce the magnitude of the jitters from the guiding pulses. So this design, from what I understand, the only kind of downside to it compared to a gem, other than it being a little bit newer, is that the range of motion, I think, is just slightly less in terms of like how far towards the horizon you can shoot with them. So the last one is the wedge mount. That basically just converts a fork mount to function like an equatorial mount by angling the base to lean parallel with the celestial pole instead of level to the Earth's surface. Rotating the base adjusts the right ascension, and rotating the fork connection adjusts the declination. So I've been talking about tracking a bit. So tracking is just enabled on your mount. Like I said before, it rotates at the same speed as the Earth, but the opposite direction to counteract its movement. If the alignment and the tracking rates are very precise, then the target should stand dead still within your eyepiece or your camera sensor. There's 3 different kinds of tracking rates. Or maybe more, but there's 3 main ones. Sidereal is what you'll use for anything on the celestial sphere. And then there's, of course, lunar and solar, which move at different rates and arcs. And you can often use lunar if you're imaging and trying to track a planet, because it follows the same arc. But technically, the images that you're taking for planetary imaging, or the exposures that you're taking, are so fast that you don't from the imaging perspective actually need to track it. You could just move it, take a bunch of images, move it again. But it never hurts to have the tracking, even in a case like that. Now, if you have perfect polar alignment, you'll never need to correct the declination over time. And if your mount has perfect tracking rates, then you won't need to correct the right ascension over time. But neither of those are likely in most cases, especially since most of us are going to use entry or mid-level consumer mounts. So to account for the errors in our alignment and in its tracking rates, we use a second camera and some form of computer for active guiding. So there's software that monitors the guide camera's image, and which is often taken through a dedicated guide scope that's mounted to the primary scope, which is what you see circled in yellow here. And what it does is monitor the star field, and if the star moves off of the pixel that it started at, then it sends guiding pulses to the mount to push it back to where it should be, staying still on the same pixel where it started. That's the kind of the high level view of how to consider what it's doing. The fewer and shorter pulses you produce, then the better image you're going to have, because it's not going to be bouncing at all. And if you have decently dark skies and ample star fields in your images, you can omit the guide scope in favor of an off-axis guider, which uses a prism, which you'll see hanging down in the circle there, to steal some of the light from your primary telescope's field of view by redirecting it to the guide camera. That can give you more precise guiding, because ideally you want your guide scope focal length to be a third or more of your primary scope. And when you use an off-axis guider, you're going to get the exact same focal length as your primary scope. Because the light traveling through your telescope is round, like the mirrors in your lens and the lenses in your scope, the camera sensor is rectangle. There's usually a position that the prism can be seated into to steal light from the round part of the light coming through that wasn't going to land on the sensor to begin with, and therefore can avoid distorting or causing shadows on the image of the sensor itself. So you can see here, this is the off-axis guider, followed by just a spacer, and then a filter wheel, and then the camera. And then the guide scope, or guide camera rather, is at the top. So on to cameras. So everyone knows about, and probably starts with, the DSLR camera these days. You can take some nice images with the DSLR, but you should recognize what the shortcomings are and how you might need to modify it. The imaging chip that's used in every DSLR I've seen is a CMOS sensor technology. The vast majority of dedicated astronomy cameras are also CMOS. So what's the difference between the two, and why is a dedicated one any better in some cases? Largely it comes down to specs and how they were designed for their intended use. So the factory install for a DSLR usually includes two filters that kind of affect what we're trying to capture as astrophotographers. The UV-IR filter cuts off UV light and shorter wavelengths, and the red balance cuts off a lot of the red light, which includes the HA, the hydrogen alpha signal, which is very prevalent from deep sky objects. But it's used in DSLRs because if you include near infrared light and UV light, you get a purple kind of haze over the image. And that's not how our eyes naturally see, because our eyes, they're not sensitive to those outer fringes of the visual spectrum. In addition, the body size and shape of a DSLR, all the external features like the screen, the battery, are all technically a waste of space and weight from the astrophotography perspective, because you're not going to be constantly looking into the camera and making adjustments on the camera itself. And in fact, you want to touch it as little as possible to prevent any shaking or moving your aim. A lot of the built-in functions are useless and need to be disabled, like anti-shake and anti-focus, and accidentally forgetting not to disable them can ruin your night. They also might apply visual optimizations that sometimes cannot be disabled, and those optimizations are intended for daytime photography, not for nighttime. Some lower end models don't even include a bulb mode, so you might be limited to what your maximum exposure can be, usually like 30 seconds or so. That's not generally enough for doing longer focal length or for dimmer object photography. The sensors are uncooled and tend to have a significantly lower quantum efficiency. And you can't always guarantee full support in the astronomy specific hardware and software for some brands and models of the cameras. Sony in particular, for the longest time, had proprietary software development kits, and a lot of the open source software that exists therefore did not incorporate those SDKs because they would have had to pay for the rights to use them. And even some of the Canons and Nikons, especially when they're brand new, may not immediately be supported. So if you do stay with DSLRs, or you're looking to buy a DSLR to get into the hobby, try and figure out which software packages you're going to use first, and then make sure that that model is going to be supported. So now from the dedicated astronomy camera perspective of CMOS sensors, they have the option for cooled and uncooled sensors. And when you're doing longer exposures, like I mentioned before, the sensor technically warms up as it's accepting the new light, coming in from these targets that you're shooting. The cooled sensor allows that that warming up to be less, and therefore reduce the thermal noise coming off of that chip. You have an option for mono sensors and one-shot color sensors. Mono sensors, if you're going to get a color image out of it, you have to take multiple pictures of the same target. Once with the red filter in front of the entire camera, once with green, once with blue, and then once with the luminosity as well. And then you combine those later as individual color channels to create the color image. With the one-shot color, you end up with a Bayer filter mosaic pattern right on top of the sensor, which is a red, green, two greens actually, and a blue squares directly on top of each pixel. That technically reduces the resolution that you're getting for each individual color channel, but allows you to take a full color image in one shot. We'll talk a little bit more about that later too. There's generally excellent cross-product support for astronomy software for these types of cameras. There's just a couple exceptions, but in most cases it's supported across the board for almost any brand. And you can do things like digital binning. I'll get into why I call it digital binning specifically later as well. But it essentially allows you to make the sensor lower resolution, but accept a higher signal to noise input from your source by putting four pixels together and considering a single pixel, a single larger pixel. That'll reduce your noise. But then there's also the CCD cameras, also dedicated for astronomy. Very similar to a CMOS camera. They generally get a better signal to noise performance than a CMOS camera. They perform analog binning instead of digital binning. With the digital binning I mentioned before, with CMOS, it occurs in the software. So it gets read, each pixel is read individually, and then it's binned in the software to create that better signal to noise. With a CCD, it's done right on the chip, and then you only have to do one read per super pixel, which keeps the read noise down more on a CCD if you're using binning. But they do tend to have slower readout times than the CMOS, so maybe not as good for a video if you're doing like planetary. They do tend to be more expensive than the CMOS, and when you try and do a region of interest, they can't do, unless it's been resolved in more newer hardware, I haven't seen it yet, they can't do region of interest in the way that you would expect it to happen. So when I mentioned doing a region of interest around a tiny target like a planet, you're trying to read just those, say, 400 by 400 pixels in the center of your sensor, and you don't care about anything else. So if you're only reading those 400 by 400, you can read frames much faster. With the CCD, it has to read full lines, and I believe it has to start at the top as well. So if you're reading something in the center of the sensor, it's got to read everything from the very top line all the way down to the bottom of the region you care about, no matter what. So it's still less than the full sensor, but it's not just the pixels that you care about. And then the other thing I'll just mention, CMOS and CCD both have the ability to sort of increase the sensitivity of their pixels. CMOS refers to it as ISO, and CCD refers to it as gain. It is technically a slightly different implementation of hardware underneath the covers. They both achieve the same sort of result in doing so, and sometimes you see the two used interchangeably when you're seeing explanations about how things work. So don't get confused by that. It's essentially the same thing. So the Bayer matrix that I mentioned before, it's a pattern filter. Like I said, it's by default well, not by default, but most commonly it's 2 green pixels, 1 red and 1 blue. That's because our eyes are more sensitive to green. But in a astrophotography world, that's kind of more used as just a luminance sort of color. There's not really a whole lot of green coming out of the universe in terms of deep sky objects. So if you have color, all 3 colors of light coming in, for any sensor, any pixel, sorry, that has a red filter over it, only the red light's going to get through. And if you were to look at your sensor for where the red light's landing, it's going to be only 1/4 of the pixels. For the green, it would be 1/2, and for the blue, it would be 1/4. Putting them all together was when your eye sees that as like a single color image, because you're not looking so close to see each individual pixel. You kind of your mind sort of blends it together. Sometimes in the software, you have to tell it what pattern you're using, so you may have to look that up with your camera to find out which pattern. And other times, it can automatically recognize it. So speaking of filters, these definitely confused me when I was kind of getting going. There's a lot of different types. There's a lot of different terminology and a lot of charts. It took me a little while to kind of figure out what I was looking at, what it was trying to tell me. So on a filters product page, you'll inevitably find a chart like this, which defines what percentage of each wavelength of light gets transmitted through the filter, which is referred to as a transmission curve. The wavelengths are on the x-axis and the transmission percentage on the y-axis. So the UHC LPR filter on the left is designed to transmit around 98% of the hydrogen beta, the doubly ionized oxygen, hydrogen alpha, and the ionized sulfur wavelengths of light, while rejecting or absorbing several light pollution wavelength sources from, for instance, sodium and mercury lamps. The range of wavelengths that are allowed through a filter is referred to as the bandpass or the bandwidth. And if it allows a narrow range of wavelengths through it, then it's considered a narrow band or narrow bandpass or a line filter, like the one on the right. If it allows a wide range of wavelengths through it, like the filter on the left, then it's a broadband or a wideband pass filter. Narrow band pass filters generally focus on specifically what you want to allow through. So a 12 nanometer band pass, like the one on the right, means it allows some of the light that is between 6 nanometers shorter and 6 nanometers longer than the target hydrogen alpha wavelength to still get through. And the hydrogen alpha emits at 656 nanometers. So this filter allows some of the light between 650 and 662 nanometers to make it through. But you can see as it gets further away from the target wavelength, the amount that it lets through drops off fairly drastically. The transmission percentage for light above or below the target wavelength drops off steeply. That's kind of desirable because that allows for a sharper, more detailed image from that light. And you may find multiple narrowband filters that are identical except for their bandpass, such as another hydrogen alpha filter that's listed as 7 nanometers. A 7 nanometer filter will isolate that HA wavelength even more cleanly, while the 12 nanometer version allows that additional 5 nanometer range around it to get through. This means that you're going to let less total light in through the filter, which is generally okay for astrophotography because you can have a minutes long exposure, but you wouldn't use a narrowband filter generally for visual astronomy because it'd be so dim of a light that you already have a hard time seeing that you probably won't see anything. The exception to that would be solar viewing. Because the sun's so bright, we have filters with band passes of just a few angstroms and can still view it directly, which is, if you're not aware, there's 10 angstroms in a nanometer. So it's a significantly narrow amount of light getting through. And that's just another chart for the hydrogen beta, the way that it looks. Same concept. So you have UV-IR cut filters. I mentioned that briefly when I was talking about the DSLRs. Cut filter has a steep cutoff point for the transmitted wavelengths, and this chart shows a cutoff that very steeply rejects anything less than 400 nanometers, which is the UV range, as well as anything above about 700 nanometers, which is the near infrared range. The UV and the near infrared, as I mentioned, are violet and red tinges that will combine and create a purplish halo or bloated stars if you let them through. So the most DSLRs, like I said, have two different filters. These are examples of what those two filters look like in terms of the light they're letting through the transmission curves. Both intend to keep the image looking truer to human sight, so you don't get those purple hues. But from the astrophotography perspective, we actually want to keep more of that light closer to the near infrared range. So the red balance filter, you can see, rejects 80% of the light that's coming through at that hydrogen alpha wavelength. And then once it gets to the UV-IR cut filter, it's rejecting another 20% of that. So all in all, by going through both of these filters, you're only letting through about 4% of the hydrogen alpha light that came into your lens. That's why an unmodded DSLR is not particularly great for photographing hydrogen alpha targets. If you can get these modded and remove the filters, or you can even do them yourself if you're careful. An Astro modded DSLR will actually have the red balance filter removed, which will allow the majority of that HA to make its way in. So you'll only be losing about 20% of the light that's coming in when it hits that UV-IR cut filter. Alternatively, you can do a full spectrum mod where it removes both of the filters. Now, without any of them, you're going to be letting in that UV and the further near infrared light, which, as I said, is going to give you the bloated stars and not the ideal. But the advantage of that is you would then reintroduce an astrophotography designed UV-IR cut filter, or another filter that has the same UV-IR cutoff specs. And those actually allow more of the hydrogen alpha light in than what the DSLR's default UV-IR cut filter will. So if we look back at the last chart, you can see that you're getting here's the 600, here's the HA wavelength is right around here. You're going to get about 92–3% of that HA light through this UV-IR cut filter, instead of only about 80% of the light getting through this UV-IR cut filter. Also, there's usually the astrophotography version will allow more of the sulfur, ionized sulfur light through, which is just a little to the right of the HA light in terms of wavelength. The LRGB filters, these are what you would use for collecting luminance, red, green, and blue filtered frames with a mono camera when you want to get a color image in the end. Like I said, you take those images with each of these filters and then combine them in the software. The pass-throughs for each of the filters are shown on here. The blue line represents the pass-through for the blue filter, the green for the green filter, and the red for the red filter. You can see they deliberately skip this HGNA line here because that's sodium lamps producing that type of output. And then the black line that follows above all of them is the luminance filters transmission line. Now there's an IR pass filter, which is kind of the exact opposite of the UV-IR cut filter we just looked at. This blocks everything except for the near infrared light. These kind of have a special case use on them. It's not too commonly seen or used, to be honest, in astrophotography, but you can find them, and I didn't really understand what they did or how they worked. But what you can see is that it very steeply, right after the hydrogen alpha, you get into that near infrared range, it very steeply starts to allow that light in. And when you combine that with a color camera, a one-shot color camera, particularly like this one from ZWO, the transmission of that near infrared light is roughly the same no matter which Bayer matrix pixel filter it's going through. So whether they're, even with a one-shot color, with this IR pass filter on it, it'll actually get a very evenly illuminated image, almost as if it was a mono camera. And so it's kind of hard to see here because I think I made the picture too small for you, but the hand in this picture, you can actually see the veins running through the fingers because the infrared light coming from those veins is prominent enough. but the image gets evenly illuminated because even though they're different color filters, none of them block that near infrared light any differently than any other one. So just some considerations with the filters if you use them. You always want to place them as close as possible to the camera sensor to avoid introducing aberrations like light reflections and such. You also may need to adjust your exposure and focus when you either introduce them or switch to a different filter, because the glass can be different thicknesses, which can cause the focus point to change, and the amount of light coming through them is going to be different. So your exposure might need to change to account for that. So you've captured all of your images. Now you're going to process them. One of the first things you're going to do is stack them. And the stacking, there's a few different algorithms for it, but what it ultimately does is align and combine all of your frames that you took into a single frame and reduces noise and enhances the signal by analyzing the pixels to look for median values across all the frames and rejecting the outliers. So there's multiple algorithms you can employ to do that, depending on different scenarios. But if you do, some of them can remove other, maybe we call them bigger issues, I guess, like a satellite streak going through one of your images without throwing out the entire frame, because it can recognize that the light going through that image is an aberration. It's not normal to the stacks that you have of the other frames that you have. You can also sometimes reduce the elongated stars if you have guiding errors, depending on which algorithms you're employing. So the one on the left is a picture. This is the Cigar Nebula again. It's a single 60-second frame on the left and 12 60-second frames stacked on the right. It's kind of easy to tell that there's a lot of patterned noise over here. Neither one of them have calibration frames applied to them yet, so it's purely just stacking. But you can see the smoother image of the background with those stacked frames, and that's compliments of the stacking process. The amp glow, which we'll talk about later, you can see that on the right, which is kind of proof that these haven't been calibrated yet. And then if we look at stacking versus tracking, both we've seen have their merits, but obviously you really want to use both together to get the best images. But just to have a comparison, the one on the left was a 300-second frame, where the one on the right was 12 60-second frames stacked together. Both of them have significantly less noise than what we saw in some of those single frames before. But when we combine all that together later, we'll see better results. The detail on the single frame is actually a little bit nicer than it is on these shorter frames stacked together. So there is advantage to doing a longer exposure in many cases. So calibration frames, I've mentioned them before in passing. The concept of calibration frames is to be able to remove imperfections and noise that are predictable from your final light frame and that are introduced by imperfections in your gear. So there's four primary types of them, three of them that you'll tend to employ. The dark frames, as they're called, remove thermal noise that's produced while capturing the light frame. That's the amp glow like I showed on the side, or as I mentioned, warming of the circuitry from doing longer exposures, as well as hot and cold and dead pixels that might be in place. The flat frames correct for uneven illumination across the image, and that might be due to vignetting, which is natural to the glass or the mirrors that you're using in your telescope, or also dust donuts. If you have dust on the lenses, you get these little dim donuts as imperfections in your image. Now you also have what are called dark flats, and I'll explain why you have those in a moment, but essentially that removes the same kind of noise that we talked about for dark frames from your flat frame. From what I've seen, people seem to use that with CMOS sensors, and they seem to use instead bias with CCD sensors. The bias removes fixed pattern readout noise from the sensor. So like I mentioned, just reading a pixel causes some noise to be injected into the values that you're getting. So how do you take them? So the number of calibration frames kind of differs by the type, and there's some rough guidelines. If you look online, you'll find a range of answers. It's not, you know, one particular number of frames is the right way to do it. But in general, with darks, you have maybe 20 to 50 frames. You use the same exposure, gain, and temperature as you did when you captured the lights. And that's because this type of thermal noise builds up over time. So the longer your exposure, the longer you want to experience that noise. And since you're trying to capture only the noise, not any light, you just want to see what the imperfections are, you leave the lens cap on. With the flats, you do about 25 frames. You do that while aimed at an even light source. And then what a lot of people have traditionally done is point at the dusk sky with a white t-shirt stretched over the front of the scope to create sort of a flat, evenly illuminated image. And then you adjust your exposure until the histogram shows that the sensor, the histogram heights are about 1/3 to 1/2 full. You don't want to fully saturate the sensor, just kind of somewhere in the middle. You keep the focus and the rotation of the camera identical because you want those dust and vignetting gradients to be exactly in the same place as they were on the lights image, so that when they get subtracted, they land in the right spot. And that one, because you're generally taking quicker images, you're not going to do a full 5-minute exposure. That would blow up the sensor. The temperature doesn't really matter. So dark flats, about 25 frames. Again, since you're trying to capture the thermal noise of when you took your flat frames, use the same exposure as your flat frames. But since you don't want any light getting in, you're just trying to see that thermal noise, you do it with the lens cap on. Or sometimes they're referred to dark frames for your lights. I've also seen flat darks as the term. It seems to kind of get used interchangeably. And then for the bias, you do 50 to 100 of those. You set the camera to the fastest possible exposure because all you're looking to capture is the noise generated from reading the pixels. You don't want any of the thermal noise to get in there, etc. And since you're taking them so fast, you don't really have to worry about the thermal noise. So any temperature is fine, but you want to keep the same gain so that that read noise is consistent with what you actually are capturing with your lights. And you keep the lens cap on because, again, you're just looking for that noise that the sensor is injecting from reading. So you can reuse these master and calibration frames, or you can reuse the calibration frames and save time by creating masters. So the noise that's generated and that you're capturing in the darks and the dark flats and the biases isn't really going to change in your camera over time. It doesn't really change much. So you can generate a library of these images, calibration images, and use them for a year or 2 years, maybe longer. But with flats, because you're talking about the dust patterns, which are going to change very frequently, those have to be taken every time you're imaging. You can compile these calibration frames get stacked just like your lights do from the software. And so there are ways to create master versions of these stacks into a single master flat or a master dark. With the master darks then, because you can reuse them, later when you take photos at the same exposure and temperature, you can just apply that one master dark, and it doesn't need to re-stack all of your dark frames, and so you save yourself time. Or if you're trying different settings, you can restack using the dark, restack your lights using that master dark, and save yourself time then too. So here's just an example of kind of how those calibration frames make a difference. So like I said, the amount of light you're actually capturing is very low compared to what your sensors can see. So a single light frame generally is black. Maybe you'll see some stars, if anything. So if you stretch the histogram, you can see that, yeah, there's actually a galaxy there. This is the pinwheel galaxy. You can still see lots of noise, lots of colored chroma noise and luminosity noise, as well as the amp glow I mentioned. So if we take a stacked image with no calibration frames, again, it's still dark. And but if we stretch it, then we can see that. You can see the image is still there. It's stacked, so it's removed some of that noise, but not everything. You're still getting the amp glow and stuff because we haven't applied any calibration frames. Now we take the master dark, I stretched that, This is the amp glow I mentioned. It looks like it's really, this horrible interference, but again, that master dark without being stretched is essentially black. So there's so much range in what the camera can capture. This is very low amount of light, but our images are so dim that we see it. So if we take the stacked image, apply the master dark, and stretch it, we can see that that amp glow is gone now. But we notice there's other issues. There's these little dark circles here, a bunch of them down here. Those are the dust donuts I mentioned. Those are imperfections because of dust somewhere in the optical train. So we generated our flat file. I did a master flat, and I exaggerated it so you could see what's in behind that master flat image. These are all these little donuts are dust on my lens all over the place. So this is that dark one I kind of pointed out before, and a couple at the bottom that were more noticeable, but these are all there too that you didn't even really see before. So when we apply that, now you can see that all of the darks have gone away and some of the vignetting has gone away. And so this is kind of the master calibrated stacked image. There's still more that you can do with that afterwards, but that's, now you're much further along, looks way better than that first started out as. So the advanced post-processing I mentioned, you take that image that I just had, you put it into something like PixInsight, and you can do further noise reduction. You can reduce star bloat. You can remove light pollution and vignetting that wasn't necessarily injected because of your scope. Maybe it was, the light pollution has its own gradient through the sky, the atmosphere. That's coming in as part of your light frame. That's not a problem of your scope, so you can't really pull that out from a flat frame. But there's algorithms within the software that can improve on that a lot. So after I ran it through PixInsight and did a bunch of touch-ups with those algorithms, this was ultimately my final image through that. So there's an artistic side to it after that. People have a preference for whether the background, the space around the stars, et cetera, should be pitch black or should have a slight haze. The argument tends to be that, they personally themselves have never seen, looked up into the sky and not seen haze because they're always looking through atmosphere. So they like to represent what it looks like to be looking through the atmosphere. I personally like to represent more what it looks like if I were imaging it from space. Some people remove stars around nebulas because technically a lot of the stars that you see in these nebula photos aren't actually part of that nebula system, far outside, far in front of you between your camera and that nebula, or maybe even way in the distance. And then there's color mapping you can do too. If you just want to make it look prettier, you can change the color mapping, or if you just want to highlight certain features by increasing contrast and mapping the colors differently, you could do that too. So general equipment and jargon. I'm going to kind of go through these. These are just things that exist that you should be aware of that can change how you're imaging or solve a couple problems. I'm trying to spend too much time on them. Focal reducer, it reduces your focal length. And by doing that, it speeds up your focal ratio and gives your telescope a brighter field of view. You do need to be careful that you use the one that matches your type of scope. So if you have a scope that's already that has like a field flattener correction lens on it, like an SCT, like my Edge HD SCT, then you have to make sure you get one that expects the light to be coming in at the angles that field correction lens is going to be, sending them down the tube. Otherwise, you'll create other issues. Hyperstars, they cost about as much as the original scope does, but it works in a similar fashion to the focal reducer in that it ends up taking, in this case of the SCT, from an f10 down to an f2, meaning you can image wider field of view and you can take more images quickly of dimmer targets. Framing, there's a formula you can use for framing to figure out if you're going to be able, like how much of a target is going to fit in your sensor or how it could fit in your sensor. It's honestly easiest to use some software. I use Sky Safari, like in this example, and you can see that my binoculars, the round view here, would fit all of the Orion Nebula, but my imaging sensors with my SCT telescope even with the field reducer. Without the field reducer is the small square, oops. And with the field reducer is the wider square rectangle. Neither one of them can fully fit the entire Orion Nebula in it. I also like to use Sky Safari to see what I missed, such as back in 1953 BC, when we had Venus, Mars, Mercury, and Saturn all would have been within one camera shot with my rig. So if I ever get to time travel, that's where I'm going first. Binning, which I mentioned before, is combining pixels next to each other to form superpixels. Kind of already touched on this, so I won't say much, but essentially it improves your signal to noise ratio at the cost of resolution. And CMOS has a bigger penalty for it because you're going to have to read, in this like 3x3 binning example, you're going to read all 9 pixels individually, which means read noise for all 9 pixel reads, even if you're treating it as a superpixel, whereas the CCD would read just a single read to get those 9 pixels read. So it has introduces less read noise. Automation, you're going to eventually come to want it. It can control your timing. It can control the light in the calibration frames, which filters you're using, when to do a meridian flip, focusing, field rotations, scheduling multiple targets, and it can even control an observatory if you get to that level, and shut the lid on the observatory if it senses rain, etc. These are some of the software packages that handle various aspects of automation. The first two kind of do it all. The other ones can do various parts of it. The Ecos and Astroberry. Ecos is kind of cross-platform, but it does run on Raspberry Pi, and Astroberry is a version of that runs on Raspberry Pi, which specifically has control from a web interface or a remote VNC connection. So you could have a machine out with your setup and be remotely inside controlling it. And then there are also standalone devices that can do basically that, just that as well, but without having to use an entire laptop, because the amount of horsepower you need to actually run that kind of setup is not very high. So these three actually use a Raspberry Pi. ZWO's ASI Air has a proprietary software that you control from an app on your phone or tablet. StellarMate uses a form of Ecos, and you can control it just like Astroberry, or it has a proprietary app as well. And the Primaluce Eagle 4 has a Windows 10 mini PC instead of a Raspberry Pi, with its own proprietary software that you can control from software on another PC also. I personally use an ASI Air, and I tend to like these standalone devices because I never liked the idea of leaving like $1,000 laptop out for the elements, especially when we're so often out there in the very cold and with potentials for rain and stuff like that. Intervalometer is probably the earliest form of automation. It's normally you'd connect this into like your snap port, a little headphone port on your DSLR camera, and it just controls your shutter. But you can configure it or program it to tell it how many frames you want to take, how long each frame should be exposed for, how much time to wait in between frames to allow your camera time to write to the SD card, etc. In most cases nowadays, we're so computerized with so much stuff, and even the DSLRs have improved so much to have their own software packages that you can run. You often can get away without an intervalometer, but if you're just looking for that level of automation and don't want to involve a laptop, these things cost like $20 or less. Filter wheel I mentioned a little bit before. It's exactly what it sounds like. You can have multiple filters, and the wheel rotates it in front of the camera. The one on the left is manual, and the one on the right is automatic, so you can control that with automation. Bortle scale is something I had to kind of learn about when I was, kind of getting past my beginner stage. Essentially, it's just how bright the sky is and what you're able to see as a result of that sky brightness, or how dim of an object you can see, essentially. The Poughkeepsie area, if you're in like the city area, is rated about a 6. The New Paltz area, where MHAA is basically based, is rated about a 5. And where we go for our star parties, the Taconic State Park, is rated about a 4. So that's why we drive 45 minutes to get out there. Imaging under a full moon or light pollution, I just assumed when I started that was not possible. There are a lot of filters out there that can do a really good job with that. Essentially, anything that's a narrowband filter, you can pretty much get away with using under almost any kind of light pollution scenarios. This image was an example from the Optolong L Extreme dual band filter, which means it's letting two different wavelengths through, but very narrowly. The bright yellow image is how it looked after 5 minutes exposure without any filter. And the one on the left is how it looked with the filter. And then the one in the top is their final image, having 23 frames, 23 5-minute frames stacked. So you can still get a lot of detail and interesting, images, even if you're under high light pollution. Meridian flips. These ones confused me for a little while, just trying to understand the concept. So the meridian is the line that's drawn from one celestial pole to the other, straight through the zenith above you. The gem and the SEM have to flip the position of the counterweight with the telescope when the target approaches that meridian to avoid the telescope hitting the tripod, because at that point, if it kept rotating down, it could slam into the tripod. But by switching over and then continuing to follow it in that same direction, it has a lot farther to go before it would hit the tripod. So it just rotates, the mount rotates 180 degrees on the RA axis to achieve that flip. Most of the automation can handle that for you. It'll do the rotation and then assess where it's pointed and find the target that you were trying to expose and carry on. Quantum efficiency. When I was looking for cameras, there were a lot of specs about the sensors that were very confusing to me, especially because it didn't seem like it was so obvious as some other consumer products, where the more expensive the product was, the better it was all around. There were, each one has a use case kind of and its own nuanced advantages. So the quantum efficiency with the digital camera sensor, it's just the number of signal electrons that get created when a photon hits it. So how efficiently it converts those photons, that inbound light, into electrons and the digital representation of that value. So higher QE is better, but it can vary across the different wavelengths. But you'll see a chart on the camera's webpage usually that kind of shows how the QE performance is. So in this example, if you had 5 photons coming in and it's 84% efficient, you're going to end up with 4.2 electrons or less, depending on what wavelength those photons were coming in at. Unity gain, another thing that kind of came up, and I scratched my head. What the heck does that mean? The ISO setting or gain setting, where one electron is converted into one digital value, the also referred to as an ADU, by the analog to digital converter on the chip, on the sensor. That's what unity means, 1-for-1. So if you get 1-for-1, that's going to give you the least noise when you're reading the sensor, and generally is suggested as the ideal value. And the dedicated astronomy camera documentation will usually indicate what that unity gain value is. Some DSLRs call it something else, but you could always look up the sensor specs from the sensor manufacturer, regardless of what kind of camera you have. Some people suggest that adding a small amount of noise by not using unity gain can actually improve the detail, and the added noise will get removed by the calibration frames in the end anyway. I haven't putzed around with it to see if I have an opinion on that, but I usually use unity gain. There's another thing I ran into called dual conversion gain. And it's a feature that some of the higher end cameras have, where at a certain gain level, a high conversion gain mode kicks in. And at that threshold, then it enables higher gain with far less read noise than it might usually have, without impacting kind of the dynamic range of what it's able to sense. So in case you see that phrase, you have a rough idea of what that means. Another one for the camera sensors, the full well or pixel well depth. Saturating a pixel, it's analogous to filling a bucket with water, and the excess overflows into the neighboring buckets, the neighboring pixels. It doesn't literally flow into those pixels, but what it does is the voltage that's generated in that one pixel that's saturated actually ends up increasing the voltage in the other pixels around it. If you have a one-shot color sensor and you blow it like that, then you can actually have color distortions, because each of the pixels around any given pixel are other colors. If it's a mono camera, it'll just look like standard bloat of intensity around what should be a sharp detail. Deeper wells are always better in that case, and enable you to take longer exposures before you oversaturate your stars. And that allows you to get more signal from the dimmer nebula areas, which are significantly dimmer than the stars. So you've always got that competing problem of dim nebulas being your main target and bright stars kind of limiting how long you can do an exposure without saturating the pixels. They get emptied, those pixel wells get emptied when you do a read by the ADC, which then converts it to the digital values. And how well it can convert that into a smooth image depends on largely the bit depth of the camera sensor. So this is another value that you'll see on the camera sensor documentations. The bit depth is essentially how many distinct shades of the sensor, how many distinct shades the sensor can record for the light that's coming in. So a higher bit depth enables you to get greater accuracy, but it also does produce larger files. But you can see kind of the difference in gradient when you go from having something like a 5-bit depth. Even though 5 is not super tiny, you can still very easily make out those striations where it has to jump from one shade to the next. 8 is fairly smooth, and 16 is even smoother. And that can show up in how smooth your nebulosities are and that kind of thing. Dithering is a term relating to reducing noise. Basically, you shift the aim of the telescope just slightly in a random direction in between exposures. And that allows for hot and cold pixels and other artifacts, fixed pattern type noise or satellite, to end up on different areas of the sensor. And because they're on different areas, they don't get compounded. They don't compound themselves into a brighter noise on your final images. And it makes it easier for the stacking to reject those outlier values. That's usually handled by your software and automation. It does add some time to how long your imaging session is going to be, because it does take time to do the dither, let the scope settle, and to make sure that it's back on, it didn't go too far off the target before continuing to the next frame. The local hour angle is something I ran into when I was trying to figure out how to look up in the sky and understand where 0 for the RA was. You could also use the local hour angle instead of the RA and use it with the declination to locate something in the sky. And if you're looking at a product like Sky Safari at the info for a target, you'll get the local hour angle as well as the RA and declination and other coordinate values for it. So the local hour angle is kind of simple because it's just the angle away from your meridian to the target in hours, minutes, and seconds. And the meridian is 0. Left of the meridian is going to be 0 to 12 negative, and right of the meridian will be 0 to 12 positive. So troubleshooting. So these are just some common other issues that you might run into, just so you have a name for them that might help you reflect on, okay, that's what I'm hitting, and now I know what to look up or what question to ask. If you've got these pointy elongated stars like this, that's called a coma. It's called that because of the comet tail sort of shape. And they're generally around the edge of the field of view and usually seen with a reflector with a paraboloidal mirror like a Newtonian. They do have coma correctors that you can add in place if you need them. That can round out those stars across the full field of view. Field curvature is when you've got maybe the stars in the center of your field of view are in focus, but the ones on the outside aren't, or vice versa. And the one on the left here, the stars in the center are focused, and the one and around the edge, they're out of focus. And on the right image, it's the opposite of that. The stars on the outside are in focus. So of course, they make field flatteners for that. If what you're imaging is always just in the center, then, and you don't necessarily need the full field of view for your image, then you don't necessarily have to bother putting in a field flattener. Also, some telescopes, like the Edge HD, have a corrector plate in the front, which already takes care of flattening that field without having to add an additional piece towards the eyepiece end. Chromatic aberration is when you have a failure of a lens to focus all the colors to the same point. So the light of different wavelengths bends at different angles as it goes through a medium. And if the glass between, through your telescope before it gets to you doesn't correct for that, you get this kind of aberration where you've got fringes with red on the left, or red on one side and violet or blue on the other side, because the light's being refracted at different angles. So they do make chroma correctors for that stuff too. Dust, again, mentioning that, some people kind of wonder sometimes, oh, they've cleaned their primary lens and can't figure out why there's still dust. There is actually a formula for calculating how far into the light train, how far away from the camera the dust may be, and that's represented here. It's just the size of the pixel times the size of the dust in your image. So if you look at the width of how many pixels that dust takes up on your image, multiplying that by the F ratio of the optical system, and then that gives you the distance in microns from the sensor. Now, the only thing to note there is some of the documentation for cameras doesn't give you the pixel size in microns. It might only give you the sensor size. So you just divide that by the number of pixels, and that gives you a size in inches usually, because they generally give the sensor size in inches. And in that case, the resulting value you get will be in inches as well for how far away it is from the sensor. Use some useful sites. Just wanted to mention this one, astronomy.tools, which is the full URL. It has a whole bunch of free calculators if you haven't been there before. It's very useful. I've used it several times, especially as I was getting started. If you're thinking about buying a camera or something like that, you do want to be sure to pick one that's suitable for your particular focal length and type of camera or type of telescope. So there's a CCD suitability calculator, which you can use for CMOS just the same. There's also, like I mentioned before, the guide scope. You want to be a certain size relative to your primary scope. There's a guide scope suitability calculator. When I bought binoculars, I wanted to kind of get a feel for how certain objects would look given the binoculars options I was looking at. Binocular calculators came in handy for that. There's a website here. There's good examples of various aberrations and explanations about them. And I think they cover a few more than I did as well. So that's one to keep in mind if you want to learn more about different types of aberrations, or you're hitting something that I didn't cover today. And that's it for today. So, we appreciate you guys watching. We do have a couple different URLs that you can follow for the different social media sites that we have a presence on. They're all pretty easy to remember. It's all at .midhudsonastro.org for Meetup, Facebook, YouTube, Instagram, and Groups.io. And that's all for today. Let me know if there's any questions or anything.
Yeah,
I just want to express my thanks for that talk.
well, I got
The
questions.
depth of your knowledge is mind-blowing. There's so many aspects to this. It's crazy.
Yeah,
And your slides were really slick, I have to say.
Glad you liked
The
them.
one slide where you had the Orion Nebula expanded by magnification was very impressive,
Oh, thank you.
as were many of the other slides. It was really great. Thank you.
Sure.
Somebody had a question, I heard.
Yeah, Steve, you mentioned that you have a certain way of figuring out what ISO you use, and I was wondering if, and then you shortly thereafter mentioned pixel saturation. Do you ever reduce the ISO to reduce pixel saturation rather than shortening exposure times? Is there ever any reason to do that?
There's a couple, like if you've got a camera that has that high gain feature where all of a sudden it makes it less noisy to go to a higher gain, the recommendations I've seen on that have been to either use 0 or that unity gain where it kicks in the high gain feature. So in that case, there could be a case made for using the 0 gain instead of just adjusting the exposure. But I've always tended to adjust the exposure myself.
Okay. And there's also, you also mentioned that, well, earlier you mentioned that it's often it's up to the individual processor who decides how dark the background should be.
Mhm.
And I guess that's really, it comes down to personal preference, but I'd like to point out that the sky is not really dark. Even if you're in space, someone did. Anybody remember? This was months back. I think there was a story about somebody actually trying to measure the blackness of space and what, why are there photons coming from deep space where we know there's nothing we know of, but there are photons everywhere.
Sure. Yep. Yep. No, that's true. And I mean, it does get into a personal preference range a little bit, because it depends sort of what you're looking to represent with your image, I guess, right?
Mm-hmm.
If you're trying to highlight the nebula, then the space doesn't matter. Or if you're trying to articulate what you think would look like, then maybe you do include some of that. But color accuracy is it's its own philosophy, really, because everybody sees colors a little bit differently, for one. And, as you get closer to these objects, if I was close enough to be getting an eyes field view of what I'm seeing in my camera, some of these things actually get more diffuse as you get closer. So, right, they're not going to be as rich in contrast as what we see in our camera pictures. So it's a whole big can of worms to go back and forth on what the right real color is sometimes. So I tend to focus more on personally making just the data accurate in terms of the structure, and trying not to add detail that wasn't there to begin with, or that kind of thing.
And there's also a caveat that if you make the sky background too dark, especially when you're talking about nebulosity or say the outer fringes of a galaxy, you can actually cut off some of that data by making it too dark.
Yep, definitely. Just like you can oversaturate, you can cut off by making those shadows too dark as well, and then you get ugly looking splotches around it there too.
Mm-hmm.
Yeah, for sure.
Quick question about taking pictures of bright objects like planets, like Jupiter. You said that in that case you use video.
Yep.
And I don't understand why the video would make, so you get a clearer image if you use video?
Well, so what happens is when you're taking video, it's saved in a serialized stream. And so instead of taking an image and cutting it into a single file and writing it to disk, taking the image, cutting it, it has this stream of data that it's receiving into a video file. And that tends to be a lot faster than trying to do a one by one. Like trying to do 30 frames in a second as individual pictures, individual frames would be, I don't even think you can, just because of the processing that it takes to kind of finish up the photo and save it. But when you're doing a stream, it streams into that buffer, and it can do 70 or 100 frames a second, that kind of thing.
So I have a very simple question. This is probably off the mark, but if it is, just stop me. I think both Jack and I and probably others have tried to get a picture of, say, Jupiter with an iPhone. And all you see is this big blur.
Bright spots, yeah.
Yeah, it's a fuzzy brown thing,
Yep.
And with no definition on the edge. So if one were to make a video, would it come out clear?
If you took the video and could isolate the frames afterwards, maybe. The problem with using an iPhone is it's compressing everything. So when you take a video with an iPhone, it's gonna save it as like an MP4 or something like that, which is a highly compressed video format, and that loses data inherently. When you take a video with like a dedicated astronomy camera, it saves it as a serialized file. It's massive, like several gigabytes. Whereas, for a couple minutes, you get like a gig of data. But when you look at the file that you're getting from your iPhone, it's going to be an MP4, it'd be a couple megabytes. So the amount of data you're missing by using an iPhone versus a real camera is significant there, as well as it might be applying its own, daytime style iPhone algorithms to do what it thinks it needs to do to make things look more clear or more, however it thinks it's supposed to look.
And also, there's the reason you use the videos so that you have multiple frames to stack, and
Right.
and more importantly, plenty of frames to throw out, because
Yep.
it's the seeing that you're trying to overcome, and many of the frames are just plain blurry.
Yeah, I tried to put a video in of my
software
shots
just
of
throws
Mars.
that out.
Yeah.
And you only use the best frames, and stacking them also, it accentuates the actual detail versus noise or blur from
Yeah, I tried to take one of my videos, my serialized videos of Mars, and I converted it to an MP4 to try and put it into the slideshow, but for some reason it wouldn't play it. And the serialized video is like several gigabytes. But when you look at what you're seeing, it's very warbly, lots of disturbance across the surface of the planet. You can see, if you kind of try not to focus on it, you can see some of the details sort of pop in and out through that disturbance. And those are the details that the stacking are able to kind of pull together from all the frames. But you're right, you throw out, you take thousands of frames when you're doing 70 frames a second for 2 minutes, and you throw out 40, 50, 60% of them, maybe more, depending on what kind of conditions you have.
And some of the best imagers aren't even using entire frames. They're only using a fraction of the frame. It looks for a little spot of sharpness and says, oh, let me use that spot.
Right.
And then just throws the rest of it away. And then just,
Yep.
it gets that detail.
Yeah.
I have a question.
Sure.
You probably don't know the answer because it's very technical. Do you have any idea when a pixel is charged, there's a voltage on it?
Yep.
Do you have any idea what that voltage level is?
No, I don't think I would know.
No, okay. That's a tough one, and it's not. You don't need to know that.
Yeah,
But
there might be some relation to it with like the sensitivity of the sensor. I'm sure you can find specs for all of these sensors if you go to the actual manufacturer's website. So you probably could figure it out, but I don't know it off the top of my head. And there may even be some way to calculate it based on the specs that they do show on most of the product pages for the finished assembled camera products. But I've never looked into it.
Well,
I know it doesn't make any difference to you.
You're right, exactly.
It either works or it doesn't.
Right.
Well, I think it's a little bit different. I mean, a pixel holds electrons,
Yes.
and an object may have just 100 electrons. Then you have to convert those electrons to voltage as part of the chip. So you can't really say how many volts are in that pixel. It's how many electrons are in the pixel.
Until you've converted it.
Yeah.
Well, yeah. I was told, I was talking, when I was at NEAF one time, and I was talking to one of the manufacturers, and he said, well, it's a charge, but the charge is actually, it's voltage times capacitance, I believe. So there is a voltage there clearly, but I don't know. I'm just curious what that level is, because you're dealing with very tiny signals. We're talking about signal to noise ratio.
And maybe there's some
signals are really
really small
small.
well depth and the, to sort of tease it out what the voltage, if it was perfectly converted, what that voltage might equate to. But yeah.
You got a problem. Last night I shot the 2.5-day-old moon, 7% illuminated, so my eye could see a lot of earthshine. And the problem is the 7% illumination is pretty damn bright.
Yep.
So I messed around with it as best I could, get something that's suitable to put on Facebook. But got any help with that?
Yeah, so normally when you're shooting the moon, you're going to want a neutral density filter or a polarized filter. And the neutral density filters, for instance, will range from like, I think it's like 1/4% to like 70% rejection. And a neutral density just meaning it's rejecting light evenly across the entire surface and across the wavelengths. It's not
You think
trying to
I'll be able to get the earth shine and knock back on the crescent?
Now you have to do
Right, yeah, so the neutral density,
multiple exposures. Very, very short for the crescent and a much longer one, and then combine
HDR.
HDR.
yeah, you could do that too.
Yeah. A month from now, I'll give it a try again at 7%. If it's
Yeah, the
good.
moon can be kind of tough because it is quite bright, but if you're trying to get foreground in there too, then it's.
Even only a 2.5-day-old crescent is phenomenally bright,
Mhm.
but the earth shine is really something that's worth working for.
Yeah, you need at least 2 exposures.
Yeah, a lot of times if you want foreground from night and some kind of night object, you do have to use special software to stitch together the foreground picture that you took at the exposure to get that to look nice, and then the background image taken at a different exposure where that looks nice.
Yeah. I'll work on
Do
that.
you have any guide or tips about, say, the exposure judgment for doing something like a nebula versus a galaxy? In other words, in the galaxy, you've got a very bright object with a lot of black in the background, and I'm just wondering, can you overcook the galaxy and lose detail because you've just exposed too long, or is that not usually a problem?
You definitely can. I mean, a good example of that's actually like the Orion Nebula, right? The center of that is super bright. Those 4 stars in the center, it's, I think, impossible to get a single exposure where you get the good nebulosity visible and don't blow out that center with those 4 stars so that you can still see the 4 stars. So almost always to see a really nice complete picture of something like that, you're going to take multiple shots at different exposure lengths to then stitch together. Yeah, the targets like that are tough for sure.
Well, the top object I'm working on is Markarian's chain, and I'm
Oh.
just starting to shoot it. And so I was looking at 5-minute exposures versus 60-second exposures and trying to decide whether I could get more detail of those very small galaxies. And
Right.
I seem to get a better result with the shorter exposures, but I don't know if I'm doing a controlled enough experiment to know if that's really why it happened.
There honestly, there's probably a formula somewhere that would kind of calculate that out. I don't know it offhand. I do know a couple of our members did recently shoot that particular target. So I don't know if anybody is on right now that wants to chime in on the exposures they used, but a couple of them came out pretty good.
I don't know any of you. I'm Sargon.
Hi, Sargon.
My first time coming, but I shot M106, which is similar, a little bit different than Markarian's chain. I do 300-second exposures, no filter, and that's at 950 millimeters focal length, so f7. I find with galaxies, I'm usually going pretty long on the exposures because there's the wisps and the faint detail is pretty it's pretty important to making it look good.
Right. Anything else? Any other questions?
Yes, Steve, Jim Webster from Astra. How you doing?
Good. How you doing, Jim?
On a modded camera, I'm looking at the chart from Spencer's, and what would be like a good middle ground modification?
I'm not sure what you mean by the shot from Spencer's.
Well, they're given like full spectrum and visible HA, 2 spectrum only, AA filter.
Oh,
There's like a whole slew of options in here.
so I don't have a whole lot of experience doing the DSLR modifications. I went from a standard DSLR and straight into a astronomy dedicated astronomy camera.
Right.
But I would be willing to bet there's a few people on here that have been using DSLRs for longer. But my understanding was always just the two that I was familiar with were the those 2 filters I brought up.
Right.
And the removal of those. I know there's a lot of filters you can get that'll just clip in that work just like a standard screw-in filter for a telescope, and so I would expect they probably have versions that would, let in specific 2 or 3 wavelengths that are the important ones for deep sky. It probably, in most cases, it comes down to what do you want to image, right? So if you're removing all the default filters and you're just adding back in a new filter, to choose which filter you add back, it's going to be a decision based on what you're trying to target and what light is emitted from those targets. So if you're doing something like, Cocoon Nebula, where it's almost entirely hydrogen alpha, then you probably don't necessarily need a dual band filter kept in there. But in a lot of cases, you're going to want multiple filters because you're probably not going to dedicate a camera to just HA and another camera to
Right.
beta, et cetera.
I would just add that if you're doing an Astro mod and you want to do clip-in filters, make sure that model does clip-in filters. I got picked up with that, so.
Good idea. Yeah, not all of them accept the clip-ins, so do be sure that you make sure that's a thing for your camera.
I think I had a Canon modded, and I think when you some of the sites that do it will replace the IR cut filter with other ones, and those are generally helpful if you plan to use the camera also for regular photography. If not, you can probably just remove it, keep it full spectrum, and put the narrowband or other filters in front of it.
Okay. All right, cool.
Any other questions?
All right. Well, thank you so much, Steve. That
Sure.
was absolutely marvelous.
Good.
And I noticed that you didn't go very far into price.
Yeah, I mean, price is such a
I want to bring everybody down right off the cuff.
yeah. The only thing I mentioned for price was those hyperstars. I've kind of had my eye on them for a while, but yeah, it costs the same amount as the entire scope. So it's like I got to really be ready to dive into that, and I want to exhaust some of the other avenues I've put my fingers into recently with the other styles before I dive into a whole new one that's going to cost me $1,000, $2,000.
Yeah, excellent. I just I wanted to mention that I took that's the one thing I was going to say. You were mentioning about making flat the whites, and I've actually been trying this out for illuminating me because it's very dark in here. There you can pull up a web page that'll give you a selection of colors, one of which is just white, and then you point your camera at your screen and take your pictures there. That was kind of useful. One of our guys used to take a iPod or one of iPhone cameras or something like that and just hold it on the end of his camera with a white screen on it, and that was a good way to do it. But I took a few test pictures of mine because a couple of you know that I was out at the Star Party experimenting with my my tracker and an old Canon D20, and basically really just wanted to find out if I could aim the thing, get it aligned on Polaris, and shoot 3-minute exposures without star trails, and it worked. It was marvelous. But didn't take any flats, didn't take any darks, didn't take anything else, just a few images. So I said, okay, well, let me just do that here. And I took some images. I'm going to have to do the whites over again based on your information, as I may have blown it out. I don't know. Could not see a single spot on it. I mean, I've cleaned my sensors before, so maybe it's stuck. I don't know. But when I took the darks, it was like I was looking at, one of these oddball puzzles. It's just, a couple of dots. It just covered with red, green, and blue dots all over the entire field. I'm like, yeah, okay. Well, the camera is very old, but that was kind of cool.
Yeah, as they get older too, they get more and more stuck pixels, and
Oh yeah.
And the quantum efficiency difference between a DSLR CMOS and a dedicated Astro camera CMOS are pretty stark too.
Oh yeah, it's got to be dramatic.
Yeah, because I mean they're made for taking pictures in the daylight where photons are rich, right? There's no shortage, and
exactly.
So when you're doing it at night, I mean it's on the order of, I think it was like 20 or 30 or 40% difference on the one I looked at in terms of the quantum efficiency level. So that also means you're taking longer images with the DSLR to collect the same amount of photons.
Yep, exactly. Very cool. Very good stuff. All right. Well, for any other questions, we'll just drift right on over into the social period of this thing. Or keep talking about cameras, either way.